Welcome back to G Fun Facts Online. Today, we are not just talking about a faster computer chip. We are talking about a fundamental collision between two fields of physics that have historically ignored each other: magnetism and optics. We are diving into the world of spin-photon transduction. This is the physics of the picosecond, a timescale so fast that it breaks the rules of how we traditionally design electronics. To understand why this matters, we have to look at the wall we are currently hitting. For the last 70 years, the digital world has marched to the beat of the electron. From the vacuum tubes of the 1940s to the 3-nanometer silicon transistors powering your smartphone today, the unit of computation has been the flow of electrical charge. We move electrons around. But as we race toward exascale computing and train artificial intelligence models with trillions of parameters, the electron is becoming a liability. It is heavy, it carries charge, and when you push it through a copper wire, it generates heat. We are approaching the interconnect bottleneck. Our processors are fast enough to solve the world's hardest problems, but they spend most of their time simply waiting for data to arrive, idling and burning power. The solution is not to make the electron faster, because we can't. The solution is to stop moving electrons and start flipping spins, linking them directly to the fastest carrier of information in the universe, which is the photon. This is the promise of spin-photon transduction. It is a paradigm shift that replaces the shuffling of charge with the flipping of spin, the intrinsic angular momentum of particles. By converting the quantum state of a spinning electron directly into a flying photon, and vice versa on picosecond timescales, we are unlocking a regime of data conversion that is orders of magnitude faster than anything in your current computer. Let's break down the physics of this, because to appreciate the engineering, you have to understand the chasm we are trying to bridge. In classical computing, information is stored as magnetic orientation in hard drives or electric charge in memory. In optical communication, information is light. Electrons are great for processing because they interact strongly with each other, but they are terrible for transmission because of resistance. Photons are the opposite. They are massless, neutral, and perfect for transmission, but they barely interact, making them terrible for processing. Traditionally, converting between these two worlds is clumsy. It is called the OEO conversion, or optical electronic optical. An electron hits a sensor, creates a cascade of charge, which is amplified, processed, and used to drive a laser to create a new photon. This takes nanoseconds to microseconds and burns massive amounts of energy. Spin-photon transduction skips the charge step entirely. Instead of moving electrons, we just flip their spin. Spin up is a 1, spin down is a 0. Through phenomena like the optical Stark effect and spin-orbit interaction, a photon can directly impart its angular momentum to an electron, flipping its spin in mere picoseconds. Conversely, a relaxing electron spin can emit a photon with a specific polarization that encodes its state. But why is this so much faster? Why are we talking about picoseconds, or trillionths of a second? The timescale is dictated by the strength of the interaction. In systems like TDK's newly announced spin photodetector, the mechanism relies on something called electron heating. When a photon hits a ferromagnetic material, its energy is transferred to the electron system in femtoseconds. The electron system heats up and changes its magnetic properties long before the actual atomic lattice, the physical structure of the material, has time to vibrate. This decoupling of the electron temperature from the lattice temperature allows for switching speeds that are fundamentally impossible in standard semiconductor devices, which are limited by how fast charge carriers can physically drift through silicon. Speaking of silicon, we need to talk about materials. Achieving this subtle quantum handshake requires materials that exhibit strong light-matter coupling. Silicon is the workhorse of the 20th century, but it is notoriously bad at this because it has an indirect bandgap, meaning it effectively refuses to emit light. The search for the perfect spin-photon interface has led physicists to exotic new platforms. First, we have transition metal dichalcogenides, or TMDs. Materials like molybdenum diselenide are atomically thin, two-dimensional layers. In these 2D worlds, an electron's spin is locked to its momentum, a property called spin-valley locking. This means you can control spin just by choosing the polarization of light. If you shine left-handed circular polarized light, you get one spin. Right-handed, you get the other. Researchers at Stanford have even demonstrated placing these materials on top of silicon and using twisted light, photons carrying orbital angular momentum, to corkscrew the electrons into the desired spin state at room temperature. Then there are diamond nitrogen-vacancy centers. A diamond NV center is a defect where a nitrogen atom replaces a carbon atom, creating a hole next to it. This defect acts like a single trapped atom, where the spin can be read out optically. If the spin is up, it glows red under a green laser. If down, it stays dark. Late in 2025, teams in Germany proved you can entangle these diamond spin registers separated by 20 meters, proving this isn't just a lab trick. It can network quantum processors across a building. And for those who want to stick with silicon, there are T-centers. These are specific radiation damage defects in silicon that emit light in the telecom O-band. This is crucial because that wavelength travels through standard optical fiber with minimal loss. Companies like Photonic Incorporated are betting their future on this, developing architectures where silicon spin qubits are natively linked to telecom photons, allowing quantum processors to be networked using the same fiber that brings the internet to your home. Now, let's zoom in to the mechanism itself. How do you actually write and read data at this speed? Let's look at the write cycle using the optical Stark effect. Imagine an electron in a quantum dot spinning down. You want to flip it to up. You don't use a magnetic field because that is too slow. Instead, you fire a laser pulse. At time 0, the pulse hits. By 1 picosecond, the electric field of the light interacts with the electron, shifting its energy levels. This creates a pseudomagnetic field that only exists as long as the light pulse is there. By 5 picoseconds, this virtual field causes the electron spin to rotate. By carefully timing the pulse length, you can rotate the spin exactly 180 degrees. By 10 picoseconds, the pulse is gone, and the spin is flipped. The whole process takes less than 20 picoseconds. To read that data back out, we use cavity quantum electrodynamics. You put the atom inside a nanophotonic cavity, a tiny hall of mirrors. The cavity is designed so that light can only pass through if the resonance matches. But here is the trick. The presence of the electron spin changes the cavity's refractive index. If the spin is up, the cavity is transparent, and a photon passes through. If the spin is down, the cavity becomes opaque, and the photon bounces back. You get a digital 1 or 0 in the optical domain, read out instantly. This is not just theory anymore. We are seeing commercial breakthroughs. In April 2025, TDK announced the spin photodetector with a response time of 20 picoseconds. It uses a magnetic tunnel junction integrated with a photonic absorber. Unlike a standard photodiode that waits for electrons to drift to an electrode, this device detects the instantaneous change in magnetization caused by photon absorption via the inverse spin-Hall effect. This targets the AI server market directly, where optical to electrical latency is a killer. Then you have Photonic Incorporated in Vancouver, who successfully connected 2 separate silicon chips using photons, effectively creating a distributed quantum computer. Instead of building one giant, unstable quantum processor, their vision is to build thousands of small, stable chips and wire them together with light. There is also Oriole Networks, a spin-out from UCL, using photonics to rewire AI training clusters. In a GPU cluster like the NVIDIA H100s, chips spend a huge amount of time synchronizing weights. Oriole uses an optical switching fabric to reconfigure connections in nanoseconds, creating a superbrain where thousands of GPUs act as one. The implications of this are massive, particularly for the energy crisis. Data centers currently consume about 2 to 3% of the world's electricity, and as AI models grow, this could triple by 2030. Moving data electrically across a chip is efficient, but moving it across a room via copper cables is terribly inefficient. Spin-Photon Transduction allows for co-packaged optics, bringing fiber optic cables right onto the GPU silicon. With TDK's 20 picosecond detector, we can convert that optical data to electrical signals for the GPU with zero bottleneck and negligible heat. This could cut the interconnect power penalty by 90%. Furthermore, this technology is the heart of the future quantum internet. To ensure security in the quantum age, we need quantum key distribution, sending encryption keys as single photons. But to send a key over 1,000 kilometers, you need quantum repeaters. These devices catch a dying photon, store its quantum state in a spin memory without destroying it, and then release a fresh photon. Spin-Photon Transduction is the physical mechanism that makes a quantum repeater possible. Without it, a global quantum internet is physically impossible due to signal loss in fibers. We are even looking at ultra-fast optical logic. If we can write magnetic bits in picoseconds, we can theoretically build logic gates that run at terahertz speeds, 1,000 times faster than today's 5 GHz CPUs. Experimental all-optical magnetization switching suggests a future where computers don't just process electrons, but process light matter states. We are witnessing the end of the electronic era and the birth of the hybrid era. The segregation of duties, where electrons process and photons transmit, is collapsing. Spin-photon transduction is the bridge. It is the picosecond translator that allows the massive, stable world of magnetic memory to speak the fleeting, light-speed language of the photon. As detectors enter mass production and chips enter data centers, this obscure physics phenomenon is becoming the backbone of the next digital revolution. The future is not just electric, it is spintronic, photonic, and entangled. Thanks for listening to Fun Facts Online.